We proceed with stereoregularity isomerism. Stereoregularity is the term used to describe the configuration of polymer chains. There are three distinct structures can be obtained, which are isotactic, syntactic, and atactic. Stereoregularity can have an important effect on chain packing. For example, isotactic polypropylene has high crystalline because of the regular structures. It can pack closely together. So isotactic PP has a melting point 160 degrees C. For atactic PP, on the other hand, is soft and non-crystalline with melting point only 75. So typical the head-to-tail configuration is dominant in stereoregularity isomerism. This is the example of the structure that have the head-to-tail. This is head and this is tail. This is head and this is tail. For head-to-head, CH3 is placed next to the CH3. So the usual arrangement is head to tail with the pendant group on every other carbon atom in the chain. This is another example of head to tail structure. This is head and this is tail here. This one is head to head and this one is tail to tail. Stereoisomerism denotes when the mers are linked together in the same way, for example, head to tail, but differ in their spatial arrangement. This really focuses on the 3D arrangement of the side chain group. So 3 configuration most prevalent, as I mentioned in the previous slide. Isotactic polymer, all of the pendant group are on the same side of the chain. All the pendant groups are head to tail. All of the pendant groups are on the same side of the chain. So basically, isotactic will produce a head to tail polymer. Syntactic polymer have pendant group occupies alternate sides of the chain. So pendant group alternate one out of the plane, one into the plane. So syntactic polymer are still head to tail. For atactic polymer, pendant group are in random arrangement. Pendant group are both into and out of the plane, no real registry. 2 additional points cannot readily interconvert between stereoisomers, which is bond must be broken, and most polymers are a mix of stereoisomer, often one will predominate. This is example of head-to-tail polymer. We have isotactic configuration, syntactic and atactic configuration, which is the placement of the pendant group for iso is on the same side, syndu is on the alternate, while for atactic is randomly. Isotactic PP versus atactic PP. Example shown here is the structure of isotactic and atactic polypropylene. Isotactic PP is available commercially. It has highly crystalline. Look at the structure here. CH3, CH3, CH3 is on the same side. The melting point can reach as high as 160 degrees C. For a tactic PP, it is an amorphous or non-crystalline, tend to produce soft polymer, and the melting point is 75. So a tactic PP is a non-crystalline polymer. So look at the arrangement of the pendant group. It is random. Okay. We proceed with the conformation. What is conformation? If two atoms are joined by a single, which is sigma bond, then rotation about that bond is possible, since unlike a double bond, it does not require breaking the bond. So conformation only involves a single conformation, which is a single shape that a chain can adopt. So the most important being rotation is about a single bond. By contrast, double bond are rigid, and the adjacent atom, which is the atom next to the next atom, are immobile or static. So only the single bond will have a conformation or rotation. The number of conformation a chain can adopt will increase rapidly with increasing in the temperature. As we can see, this figure is a rotation of a trans. It is a rotation of gauche, which is the bond here is adjacent to bond here. So when the rotation happens, this CH3 will rotate to be here. This example is for the rotation of trans, whereby the position of CH3 here and here. Okay, one position where this one and this one are in the opposite direction. So it's known as the trans conformation. This one, when they are adjacent, is known as a gauche conformation. You can refer to this YouTube for details about conformation. Okay, conformation is the ability of an atom to rotate this way relative to the atom which is joined is known as an adjustment of the torsional angle. If the two atoms have other atoms or group attached to them, then configuration which vary in torsional angle are known as a conformation. Since different conformation represent varying distance between the atoms about the bond, and this distance determines the amount and type of interaction between adjacent atoms or groups, different conformation may represent different potential energy of the molecule. Triple or double bond are very high barriers to rotation. Motion is largely confined to simple torsional vibration about this bond. So conformation only involves a single bond. This double bond and also a triple bond, they have a rigid. Adjacent atoms are immobile, which is static. The absence of interaction between non-bonded atoms causes the free rotation to occur. Free rotation allows the chain to take an enormous range of shape or configuration. For example, is molecule of ethane. Molecule of ethane, it has single conformation that allow um, for the chain to rotate. The conformation where hydrogen atoms on the different carbon atoms are closest together, which is in the eclipse conformation, is much less favored than the conformation where they are furthest apart. When atom distance are short, repulsive force will dominate. A Newman projection, a Newman diagram represents the torsional angle of a bond. It shows the orientation of group around one carbon in the backbone relative to the next carbon. Okay, as we can see in this figure, this is the carbon and the carbon atom is here. The rotation shown by Newman projection is the rotation of the side group of ethane. Okay. So the Newman projection for this for ethane. Okay, sorry. This is the Newman projection for propane. Okay, Newman projection changes depending on how you look down the carbon-carbon double bond here. Okay, it will also change as the carbon-carbon rotation. Conformation isomerism involve rotation about the single bond. So although there are 6 sigma bond, 7 bond in propane molecule, rotation about the 6 carbon-hydrogen bond does not result in any change in the shape of the molecule because the hydrogen atoms are essentially spherical. Okay, dalam bentuk spiral. Rotation about the carbon-carbon bond result in many different possible molecular conformation. So Newman projection will look lengthwise down a specific bond of interest. So in this case, the carbon-carbon bond in propane. So by looking from this side, we're looking down at the carbon-carbon bond. And by this side, we're looking at this carbon-carbon bond. So, 6 carbon-hydrogen bond are shown as a solid line protruding from the 2 carbon at 120 degrees C angle, which is what the actual tetrahedral geometry looks like when viewed from this perspective in two-dimensional network. So, lowest energy for propane is in the staggered conformation. Okay, this is the staggered conformation. Staggered conformation whereby the hydrogen, this one, and this one. The atoms are adjacent from one another as shown in the above projection. They are in a staggered conformation. If they line up, one in the front of the other, so they are an eclipse conformation. So eclipse propane is also known as gauche, while staggered propane is trans. So